which you caught me off guard yesterday. I did not know you worked at Morrison Maierle. So the real world's 3D, right? And we need to look at it in 3 dimensions. That means we need to look at the outer plane, right? The z-axis. We're not going to just consider stuff that behaves in a membrane action or in plane, right? Plane stress. We're actually going to allow ourselves to have out of plane loading, right? Through thickness behavior. And so what does VA use, right? We're just gonna jump ahead. Okay, I'm not gonna do any derivations of these elements. I'm just gonna show you that visual analysis, what they use is an element that provides degrees of freedom on each of our 3 nodes, right? Rotation in the X and Y axis. So that would be kind of bending, right? The bending directions. And then on top of that, you have out of plane displacements. Now you get that displacement in the 3rd direction. Constant strain triangle just had it in the in plane direction. Now we get the out of plane direction. And then also at the centroid of this element, they add 2 additional degrees of freedom of overall rotation of the element in the 2 axes direction. So rotation about the x-axis and rotation about the y-axis. Okay. The reason why they did that, okay, we're gonna do a little bit of this, right? Wave your hands a little bit. The reason why they selected all of these degrees of freedom, right, especially the rotations in the centroid of this plate, is to provide additional, right, generalized degrees of freedom, which allows us to select additional terms in our field function, right? With respect to, in this case, we're going to probably have a field function as it relates to displacement, right, in the transverse direction. That's what, oh, this is the wrong paper. This guy right here, okay, based on all of these degrees of freedom, okay, this is our beautiful equation for our displacement function, right? This gives us the displacement anywhere in the field based on our shape functions and our nodal degrees of freedom, right? So psi 1s and all of those are our shape functions. This thing just like not on. Sloppy. Okay. So they go through. Again, pretty cool. We could follow this, right? Start out by giving us a constitutive relationship. That's our D matrices. We've got our strain displacement. We have our potential energy function, right? Integrating this constitutive relationship. This is our strain displacement matrix, B bar, stiffness matrices. You get all of the contributions from strain energy, work, right? And so they derive an element that now has essentially 11 degrees of freedom. Come on. And how does visual analysis incorporate this? Well, as you can tell, all the degrees of freedom for this element are different from the degrees of freedom of the almond triangle, right? There's no overlap between it. So what does VA do? Well, it essentially smashes these 2 together. So if you have out of plane loading on a plate, well, it's going to use the equivalent energy forces using this derivation, right, through thickness displacements. Okay, you're going to have shape functions that allows us to take out of plane loading, like loading in the z direction, right, and split it up to our nodes, which would then create out of plane displacements, rotations in our x and y, rotations of the entire element itself, right? And so if there's kind of a decoupling, right, you could essentially have through thickness behavior or in plane behavior or a combination of the 2. And so in VA, I'll show you next week, okay, when you analyze a model, you can then check a box which then says, hey, I'm only going to look at in plane, right, membrane action only. And what does that do? Well, it gets rid of the ability for visual analysis to calculate anything like this. What also it does is it limits your ability to load the plate out of plane too, though, right? You might get an error if you loaded it out of plane. What does that do? Well, it can simplify our analysis, right? Because if we have that box checked and every one of these plates, regardless if we have load on it or not, it's going through and it's assembling a stiffness matrix for the entire model, right? And so this can be ways to reduce the intensity of computation that the computer has to go through, right? Reducing time, hopefully. So visual analysis combines the elements, but allows you to remove it. And they have this huge ass derivation, right? So if you wanted to have a little nighttime reading, okay, provided some for you. Okay, Brandon?
So VA uses these almond triangles, but
Uses the almond triangle and this thick, thin triangular plate element.
like, do you think that's pretty common of most modeling programs that like?
I'm not sure. I would,
Because none of like the jobs I talk to, like, they haven't heard of VA and stuff, like, so they're like, what modeling programs do you know?
yeah.
And they use these, so I'm wondering how much like VA might translate over to like other programs.
I mean,
Or like this understanding, I guess.
I talked to John Lovegren yesterday, he's an engineer at DCI, and I'm gonna have him come in and go through RAM, but it is very similar. I mean,
would assume, right?
yes, I mean, the derivation is, I mean, I'd say there's different levels of what I'd call black boxness of a program,
Yeah.
right? So my experience with RAM, which is very limited, I felt like it was way more black boxy than visual analysis is.
Push a button and get an answer?
Yeah, you push a button and get an answer. You say, oh, I want to do nonlinear time history analysis. Boom, there it is, done. I get a bunch of answers. Do you feel like it's a little black boxy? Madison? Yeah.
I don't actually have to do very complicated things, so I don't know. But
Okay.
I understand just the way that I've used it so far.
Yeah.
It's got a better GUI, doesn't it? Isn't it a lot prettier, the software?
Yeah, I would say so. Yeah.
VA is a little.
Yeah, 'cause it's-
It looks like a
Yeah,
kid.
yeah.
It's like,
I'd say
we would
visual
put the
analysis
square
is
in.
more raw, right?
Yeah.
Pure, okay?
You ever used EnterCalc too?
Oh yeah.
Oh, that is
EnterCalc
the
looks old
word.
as shit.
Oh, it's like Morrison Merrily, Kurt Keith at Morrison Merrily was the first license. We have like the license key at the top of EnterCalc. If you look at it, it's like K, they'll say something, it's like 0000001 at Morrison Merrily. Like it's been around a long time and yeah, I agree. I don't think that they've
They don't
updated
update
it
it
much.
at all.
And there's
The
some-
newest one, it still looks, the graphics the exact same.
Yeah, and I always got I don't know if you use it for footings very often.
We do, it's like super simple.
Yeah, okay, because as I say, it has scared me on a couple of occasions because I've like been like, this is wrong, you know, so like when you get outside of the like beams and columns and stuff, I got a little nervous about using it for some of the other
Why?
modules. Because I can't remember, I can't pinpoint it, but there was something with like combined footings and like biaxial bending and stuff that you can do on there that
Yeah.
when you get to like more complicated problems, it is trying to simplify everything and it's not maybe capturing the behavior that I think it should be. And so
They just added a new like 3D FEM module on.
Oh, they did?
Four
Okay.
footings.
Oh, really?
Yeah.
Yeah, so maybe that they've
I haven't used
tried
it.
to, I usually would do footings in visual analysis. And then like do like a plate model with like the columns coming down and all that stuff. And then you get your forces out of the model, right? Out of the footings, moments, shears and stuff. And then you would just go back and design it by hand. Because as you guys know from concrete, I mean, it's not that hard to design a concrete. I mean, it's essentially one way or two way, right? Action in a concrete slab, right? You have punching shear, you have one way shear, you have one way bending, right? In two directions. So it's pretty easy to, you do some minimum steel calculations. It's pretty quick to do it by hand.
You do quick RWall at all?
Yes. Yeah, a little bit,
Yeah.
a little bit.
There's some weird stuff that goes on with that, in my
Yeah.
opinion, on like retaining walls and.
Yeah. So another IES, right, is a big software, I mean, not a big software company, as you mentioned, like not a lot of places use it, but it's like, it's big in a sense that it has a lot of different software packages that it offers, okay? Maybe we'll go through that next week, but, and a lot of different companies have their, style and their types of little things to say like, IES provides a quick retaining wall program. So it's like a very simplified, if you look at a retaining wall, you guys have all taken the concrete class, right? You guys have you taken the concrete class? You designed a retaining wall, right, in 400 or 500 level concrete, okay? It just simplifies it down there. You have your active or passive pressures, you have at rest if you decide that the wall's not moving, all of that stuff. You have your sliding friction resistance, all that it takes into account, it'll design it for you, right? They also have like base plate design, you can do it that way. I think Visual or IES does like anchorage calculations sometimes too. All sorts of stuff. Shear walls, concrete shear walls, very helpful, especially when you get into like, you guys all took concrete too? Assume so, no? Not yet. Some of you have just gotten into this, right? Okay, well, you guys are gonna take it from me, so get ready for that.
Are you teaching it next semester?
I'm teaching the concrete next semester, yeah. Who's gonna be in it next semester? Yeah! Okay? It's party, huh? It'll be fun. I'm kinda jacked, I hate concrete, it's not my favorite material.
I took one with fair.
That's next fall. That's this fall.
Concrete one is
Two
next
in the
semester,
spring.
and then the next one is
So
concrete
yeah,
two.
you're not-
I need to take two.
Which one are you
I'm taking
teaching?
it next semester.
I'm teaching structures
Good
two,
luck.
and then the 400 level
I'm taking
concrete
some
next
kind of
semester.
concrete class next semester in the fall.
And then I'm gonna teach the
Structural
concrete, the next concrete the following semester.
So what are
Hopefully
you
none.
teaching?
How often,
Structures two, and then concrete one,
Oh,
I guess,
then
or the senior level concrete.
I won't.
400.
you're not teaching the 500 level?
I will the next semester, it goes in
500 's not till
sequence.
spring.
Well, whatever, I'm taking something.
Taking something, I hope so, something to graduate.
Two next semester, I'm taking.
How did we get there? Huh? How did we get to that?
We're talking about, talked
Oh,
about.
so, yeah, so like shear walls, if you guys did that in concrete, right, you have boundary conditions, like boundary elements, pain in the ass, right? So that's where VA will step in, you have to find like the plastic neutral axis and shit like that, so that defines whether or not you have these big boundary elements that you have to create, right, big dog bone, and you gotta like confine all of that, you have all these crazy ties and shit like that on the ends, right, pain in the ass, so it's nice to have a software package that helps you along.
You use Retain Pro. Have you ever used it?
I have not used Retain Pro.
If you're retaining
Okay. That's how the big businesses do it, huh? Retain Pro, huh? We're just a bunch of hicks from Montana who use visual analysis, okay? Yes. So anyway, yes, they have a lot of software. Maybe we'll go through that next week. So that was it for visual analysis stuff. To round this out so I can test you on everything possible, I've got a little bit of a conversation about equilibrium, compatibility, convergence, and symmetry.
it. Is this new notes?
These new notes, so these are out on D2L. Thank you, James. Look at that defense right away. Huh? Finally. I did post it.
Well, I'm
I
not-
posted it a while ago,
All I
too.
know is I just added them to mine at least on Wednesday, but they've been out for at least.
A little while. I think Monday is when I did them. So, just a FYI, okay?
Be like Brandon today then?
Yep, just be like Brandon. Actually, I posted these in their entirety. You don't have to write anything, okay? Because I'm trying to go fast, but in reality, I feel like I'm going slower. But so we have equilibrium, right? So we have, if we're going to look at equilibrium, we're going to look at equilibrium at different levels. We have intra-element equilibrium. What is that?
Inside.
Inside, right? If you got a commercial driver's license and you got a intra-state license, that means you can only drive commercial vehicles in the state of Montana. A little tidbit, right? Sutton, I need something like that next time, okay? No one knew that. Sutton, are you here?
I'm here.
Okay. Man,
Deep in notes.
he's deep in notes. That he doesn't have to write anything. Okay, so intra-element equilibrium. What does that mean? Well, in general, a differential element within a finite element is not in equilibrium since the displacement field upon which stresses are based is approximate. Right. What does that mean? Well, we're guessing at what we assume the displacement is going to happen between the two nodes, right? And when we make those guesses, we know that we're making concessions about that, right? We're not going to be exact. We're not going to be matching what the real world's going to be, let alone our mathematical model, okay? And so what ends up when we do that, so if we look at an axial bar, right, with a uniform load, like uniform axial load, we had a linear displacement assumption. Well, that linear displacement assumption resulted in this constant strain and constant stress. Well, how does that work, right? If we were to cut a differential element out, now we have this applied uniform load, but we're having the same force acting, right? Because the area is not changing, it's prismatic. And so the sum of the forces in the X does not equal 0, right? So we get this weird issue where we will not have equilibrium within the element because we're making these assumptions on the displacement function, and that results in this instance for the axial bar, right, inaccuracies because we're going to say that it has constant stress, right? It might have constant stress, but in reality, if we were at the end of the bar, that stress should be 0, right? But we're not going to have stress equal to 0. We're going to say that that stress is constant across the entire bar. So that that would result in not having equilibrium, right? Elias, you look like you don't believe me.
Well, but you do overall, right, like like the whole bar element.
Well, so that, yeah, so that would be
Because if you
outside,
take, like,
right?
a little chunk of
Yes.
it, then that chunk would not
Yes.
have equilibrium.
Which would be intra-element within that element, right? Inter-element, right, between elements, in general, equilibrium is not maintained between elements, and stresses depend on nodal displacements not associated with the boundary, right? Same goes for that axial or bar element, right? That stresses that we calculate, that's based on the displacements of the two nodes of that element, right? And there's two nodes, if we put two axial bars next to each other, there's two nodes that are not related to one another, right? They're only common at the one node. And so the stresses that you would see in those bars would not be the same, and so you get this jump, right? And we know when we looked at the first homework assignment, we were looking at that axial loaded concrete column, right? We want to get convergence eventually, which we're gonna talk about. And so we make those elements smaller and smaller and smaller, right? Which makes the jump smaller and smaller and smaller. That would be the hope, is that we essentially discretize the model sufficiently enough that this inter-element equilibrium is very small. But we're not gonna have equilibrium, right? If we had two CST elements sitting next to each other, right? The stresses in one element are not gonna equal the stresses in another element, right? Because the stress in one element is gonna be a function of this node that's not a part of that line, right? Because the stress, displacement is different, right? We're looking at equilibrium, which is forces, which is stresses. And so the stress in this element is a function of all of the nodal.
Would you have compatible stresses just along that edge of the nodes? of the-
No, because the stresses are constant across the entire element, right? If we looked at a CST plate, right? So you're gonna get this jump. So it's not gonna be this nice smooth transition. Nodal equilibrium. Well, we should always have nodal equilibrium, right? That's what the whole premise of the finite element method is. Those are our fine, our discretized points, right? That we then assume we have equilibrium. That's when we develop our F equals KD equation, all of that stuff. So we should always have equilibrium at nodes, since nodal equilibrium is the basis of element assembly, right? We're saying that they're equal at nodes. If we look at displacement compatibility, right, again, looking intra-element within the element, okay? If we choose continuous displacement functions, we will have compatibility within the element, right? It's gonna have a nice smooth transition along the element, as long as it's not like a piecewise function or something where we would get steps, right? It's continuous, you're gonna get compatibility across the element, which we try to always do that. Inter-element compatibility, well, that would be the compatibility, as you were asking there, right? Of what's going on along the line. Well, if we're looking at displacement, then yeah, we would have it as long as we choose an element with which it is only a function of the nodes along that line, right? And so if we've connected a CST to a CST, we know that a CST, the shape function's there, right? The shape function along the boundary between two nodes, that third node shape function becomes 0, right? And everywhere along that line, those other two shape functions sum to 1, right? So if we connect a CST to a CST, we don't have any gaps. If we connected a linear strain triangle to a linear strain triangle, we wouldn't have any gaps. But if we connected a CST to a LST, right, a constant strain triangle to a linear strain triangle, right, the displacement for a linear strain triangle is a quadratic, right? Our constant strain triangle is linear, so this line is always going to be straight, right, even when it's displaced, where a linear strain triangle is going to do something like this, and these boundaries are not going to be compatible, right?
With a linear strain triangle, can you ever have inter-element equilibrium, like stress, I guess, equilibrium, inter-element?
Oh, like
You're
a-
saying you have that constant stress in each element, but if you have a linear strain triangle, wouldn't you have
You might, yes.
linear changes
I
in
guess-
stress, and then you could have compatibility?
You could, yes. Because you would have the ability, you wouldn't have the jump.
Yeah.
You wouldn't have the jump.
Would you ever have a CST next to an LST? Like, wouldn't you were modeling
Not
with
usually.
one, you would model it all with one?
Not usually. But all this is trying to highlight is element selection is important when it relates to inter-element compatibility, right? So it could be, you could take an almond triangle and slam it next to it, you know, some other derived element. There's thousands of these out there. If you guys were in Ladine's class, right, in ANSYS, and you go to select, I mean, there's so many elements, right? And they all have their own assumed, right, degrees of freedom, which relates back to how they assume the field function, right? How it relates across the field between nodes, okay? And so it's important to think about that as it relates to inter-element compatibility. And if you did decide that you wanted to switch elements, maybe you had some weird stuff going on. When I modeled the spreader bar in that class, right, I modeled how shackles were sitting inside the holes on the spreader bar, right? So you have what we would call contact elements. They can only press against another element, right? But I didn't use those contact elements everywhere, right? So I had to take into consideration, I had to make a transition between elements, right? I wanted an element that could make that little touching between the spreader bar, right? I had a hole in our plate, and I had a pin, and that pin was putting force on, say, this larger element. And I wanted to make sure that we captured that behavior right here, in the fact that this is only going to press on, it's not connected, but it can push on it, okay? But out here, I'm gonna be looking at other things, right? So you wanna just make sure that you take into consideration what you're trying to get out of it, right? And then also how that's going to affect your results, right? Between these elements, what's going on.
We do that in ANSYS.
Yeah. Pain in the ass.
Yeah.
What a pain in the ass. Yeah. Right? For bending elements, this compatibility also applies to slopes, right? If you had multiple beam elements sitting next to each other, depending on the derivation of their field function, right? We assume that we had a cubic, right? There's other beam elements out there that have different displacement assumptions. And they do that because they're trying to find something specific, right? There's some result out of it. In our case, that's a very common beam element. I assume in RAM, RISA, like all of them follow the variational beam element that we derived, okay? Be my guess. We're using a cubic. Okay? But that compatibility would also apply to slopes, because the slopes being the derivative of displacements, depending on that displacement function, you might get kinks or steps in that slope as we go from one to the next, based on the derivation of it. All right. Equilibrium, compatibility, convergence, all right? A guarantee that as the number of elements is increased, we will approach the true solution, neglecting computer truncation and round off areas, right? We talked about computer issues when we are calculating things, the fact that we can only go, Adam talked about in class 2, right? You can only go to 16 digits. If they go to 16 digits, well, in some cases we have computations that have, say, 333 out on into infinity. Well, we're not going to be able to capture all of that, so that creates error. When we do integration, we also can get error, right? We can't integrate exactly in a computer. We do numeric integration, right? Gauss quadrature sort of stuff, where we would then make an assumption or make a approximation of a definite integral by calculating the actual values at given points and then doing some weighted sum of them. That's what Gauss quadrature does, right? Oh, Gauss, what an ass. Right? Okay, you're lucky we didn't even go into this. If I were to, some of like Dan Van Lushen or Stordahl's notes, he loves variational calculus and like numerical integration. So, hey, you're welcome. I'm shielding you all from that. All right. Didn't get a thank you. I didn't hear anything.
you.
There it is. See, thank you, Aaron. Man.
Does that mean we get an extra down test because he said?
No. No, not there yet. Not there yet. Okay, convergence, right? As we get closer, we're going to get closer to the real result, right? What's the criteria? Well, the displacement field must be continuous, okay? We need to have that compatibility across the element. We also need the element must be able to assume a state of constant strain, okay? Elements must be able to undergo rigid modes without straining. Okay, we need to be able to just move your model, right? Move those elements without strains getting induced into the element, right? You do a rigid body mode. An element's coordinate system should be invariant geometrically, right? It has no preferred directions, okay? You can't want to perform one way in one direction and differently in another direction, okay? Or want to go in one direction. 2 through 4 usually can be obtained by choosing a complete polynomial, right? And we talked about Pascal's triangle, Pascal's pyramid when you guys were doing homework 2, right? So what does that mean complete polynomial, well, that would be basically trying to take an entire triangle off of Pascal's triangle. Okay? And that has been known to promote convergence, right? Essentially saying that we can have a state of constant strain, the element can undergo rigid body modes, and then there's no preferred directions, okay? Right, if we got rid of one of these polynomials, right, or one of these terms, right, it's gonna be dominated by one direction or another, right? X is gonna have more weight than, say, y, if we got rid of the y squared term. So we try to avoid selecting, and we also try to absorb, if completeness cannot be obtained, we should try and avoid selecting higher order terms in favor of lower ones, right? We get a higher contribution from lower terms. Okay? Inter-element compatibility, edges are only a function of the nodes on the edge, right? If we didn't have that compatibility, the ability to get convergence is gonna be kind of tough, right? Because you're not gonna have that inter-element compatibility as we go across. Geometry must be properly represented. Right? Obviously, if we're trying to match an exact answer for a mathematical model, right, which is a simplification of the real world, right, we want to model it geometrically properly. Right? We need to model what's going on. And so we need that for convergence. And then elements should not be softened by low order integration. When we assume a displacement function, right, a lot of times we end up imposing stiffness within our stiffness matrix, right? Our element's overly stiff. For instance, for a beam element, we know that it should be a fourth order. It's a fourth order differential equation. So the displacement, if we have uniform load or load that acts between the ends of our beam, right? Our displacement curve should be actually a fourth order polynomial, right? Based on our degrees of freedom and our generalized degrees of freedom, we can only use a cubic, that's what we use. Right? So that's a little bit stiffer than what it actually is, right? So we have some imposed stiffness, right? And when we do lower order integration, right, that's essentially, we're gonna get back to Gauss, right? When we do numerical integration with like Gauss quadrature, you essentially, your accuracy for calculating the integral of something numerically is based on how many points within the domain of that definite integral you calculate an actual answer, right? And then you weight the sum of those to get the real answer, right? And so if you do, say, 2 points of integration, obviously you're only gonna calculate 2 points of actual value within that integral. And then if you sum those weightedly and then you said that that's your answer, that's gonna be not as accurate as doing something like you took a 10,000 integration points, right? So then you're essentially really calculating all the points along a curve, right? If you had, this is your definite integral, you might calculate 2 points, right? Do Gauss quadrature, and then you're gonna say, okay, the integral of this whole thing, and you're gonna base it off of just calculating 2 known points along that curve, right? If you did 10,000 of them, well now, holy shit, you basically have done the whole curve, and you're gonna be really close to the real answer, right? Well, doing 10,000 points is a pain in the ass, right, in the software program. It takes a lot of time. Right? We want to minimize computation, and if it's doing that, right, for every load that you put in VA on a plate element, and then it needs to take that because it's doing an indefinite integral for like our equivalent energy forces, right? And so every time it does a definite integral, it's going to use Gauss quadrature to do the numerical integration of that. In order to do that, if we did 10,000 points, well, every one of those plate elements, now we're going to have to do that. So in finite element analysis, we try and minimize this. So we try and do low order integration, okay? And we try to pick elements that are not softened by that. And we won't go into too much detail, but I would just say that we can. Yes.
How does, you saying that we use a cubic shape function instead of, which should be a quadratic function for the displacement along the beam element?
Yep.
And that adds stiffness? How does that add stiffness?
Because you're losing a contributing term, right? Because it's really your displacement function should have a term in it that's to the fourth power, that's contributing to the displacement at any given point along the beam.
Right.
Okay? It's only going to be exact in a beam sense. We went through it in the notes. It's only exact in a beam sense if you didn't have any uniform load between your endpoints of your beam.
It shows how displacement changes along the element.
Yep.
But
and
like
so
having it be cubic instead of quadratic,
because
that
you're
adds stiffness.
Yeah, because it's you're losing a contribution along the length based on another term. It's a way higher order term, right? You're not gonna add as much stiffness because it is gonna be taken to the fourth, but it's still like you're losing a contribution. So instead of like at x equal to 3, your displacement, you know, based on your cubic might be 1.2. Well, if you added it, if you used a polynomial to the fourth degree, it might be 1.21, right? It might end up being, it might have displaced more because you lost a contribution from one of the terms, right? It's really a fourth order polynomial, not a third order.
So you're refining your mesh, but at an elemental size?
I guess so. You're essentially losing contributions that are actually there.
I feel like it could go either way, you could lose stiffness or gain stiffness. Right, it's just the way it varies.
Yeah. I don't think so.
No?
It's like an extra way to displace, right?
Yeah, yeah,
It's
I mean,
like an
it's-
extra mode shape.
Yeah, so instead of, you're essentially losing a contribution, so it's always going to change the displacement in the, like, opposite direction. Like, you're gonna be pulling back, it's gonna make it stiffer, I guess. I can't really think of a better word to like.
Yeah, I'm just like saying if there's that like an assumption you should make that it's a little bit stiffer than it actually.
It is an assumption based on our degrees of freedom and our generalized degrees of freedom, like, we can't model the actual displacement within a beam because we're limited based on the degrees of freedom we have based on the derivation of the element. And so we lose a contribution is essentially, that's the best way I could put it. Yes, Max?
So in ANSYS, we like picked if we were gonna use like a plane 42 or like whatever type of element we're using, but in VA and other programs, they just pick.
They usually, like in structural engineering programs, they have elements that are pre-selected. So you're gonna like say, I wanna model a beam. Well, when you say, I wanna model a beam, they have a beam element, and that's the one element that they use.
And then that, they make sure that it does all this stuff and then.
Yes, well, that element has been selected in such a way that we try and use a complete polynomial. We try and make sure that it has attributes that help with it with respect to convergence, right? It's all, they selected that element based on the fact that we are using this software for structural engineering, and what we're trying to get out of it, that element is the best for that. And so, yeah, I mean, I haven't looked at the help file for RAM or RISA, okay? But I'm assuming they use a beam element that is used in visual analysis. Plate-wise, they might use the Ullmann triangle, okay? They might use this thick-thin derivation. I don't know. They might have decided to use a different one, depending, okay?
But then, so is ANSYS more for like mechanical or?
Everything.
Oh.
Heat transfer, like all sorts of crazy stuff.
Is there a way to
Yeah.
write code for visual analysis and have it run?
I don't think so. Like pull up like a script file and like,
Yeah. Did he-
I don't know. You would make Adam's day though, asking that question.
So you have it-
But it's not that much, I mean, I don't think Adam would actually show us because it's like proprietary, you know? You
Yeah.
might bring a camera out and take a picture of it. But like, I'm assuming the code is very similar to, in general, to what we've done in class, right? With our truss, or like what you've looked at with respect to Ledeen's. I mean, the process is there. I mean, you're having a assumed displacement function, right? You would figure out your shape functions. From your shape functions, then you can figure out all your stiffness matrix, you know, like you essentially, then you can assemble everything. I mean, everything is there. You pose boundary conditions. And that's all it is back there. I'd be really interested to like see the code, the matrix, if you will, like what's going on. I think a lot of the code really is like doing the user interface has got to be a pain in the ass, right? Doing the code checks also has to be a pain in the ass, right? You're taking the steel manual
I don't know how
and you're
much
trying
they
to
actually
impose
do.
it.
Like, does it have everything in it?
I mean, I wouldn't say everything. I'd
But
say
I always, like, I take it out, I still, when you do it, I take it out and I put in like EnterCalc or something else, cause I don't like trust.
That's
it.
good. That's awesome. That's fine. At some point, hopefully, you would gain some confidence in the software
Yeah.
by checking it one way or the other, and then maybe you would then lose some of that extra time based on the fact that, okay, I do feel comfortable, I've done this a bunch, I can just use VA, I don't have to double up and do the analysis twice.
Until you find one error and then have to double check it every time.
Yes, until you find one error, then you're always double checking it, for sure. Okay. They've come up with a test to test 2 through 5 up above. 2 through 5 is right, we had that stated constant strain, it can go under rigid body modes. It has no preferred coordinate system, and it has inter-element compatibility, and it's called the patch test. What do you do for the patch test? Well, you form a mesh, has at least one node surrounded by elements, okay? So an example of a patch test, you would take your elements, you select you could select, if you wanted to check some of the requirements for compatibility in ANSYS, for instance, you were modeling something, and you knew you were gonna model it out of plates, right, for instance, you could do a patch test to confirm that we had continuous, constant strain, rigid body modes, all of those things. You, as a user in ANSYS, could just make this model if you were doing plate 42, plate 352, or whatever you ended up deciding. Okay, you would create this model, you'd apply either forces or displacements that would result in constant strain or stress, okay? And then you would verify all elements are at constant stress at all locations, and you could confirm parts 2 through 5, okay? What does that mean? Well, so like you would impose forces on those 3 nodes. In order to get uniform forces, you would put, a unit force of 1, 2, and 1. If you want to do displacements in order to get constant strain or stress, you would just want to move those over the same amount, right? So you do a unit displacement of all 3 nodes. What does that look like? If you did it in VA, what's this thing right here? So in VA, if you were to display stress, right? In order to have constant stress, right? So on each one of these nodes down here, you either apply a force or a displacement, yes?
When it says split plates and it says X plates and Y plates, which is which?
Split
When
plates.
you're like splitting,
Backwards.
I'm sorry, this is always, I've never known, and I always have to like do it twice because I do it the wrong way the first time, but it says, like split plates and like how many do you want in the, like, it says X plates and Y plates. Is that based off of your like local coordinates?
Usually.
Okay.
Yep.
Can't you over refine a mesh? I feel like in FEA, we got to a point where we had like a cantilever beam and we refined it to the point where it got to the exact, but then you refined it like almost too much, you'd start to vary and then go way off from the actual solution as you over refine.
I guess
There's like
as
weird things of like where you apply the force and like those elements near that force with a super
Oh.
refined mesh. I remember like,
Yeah, that's different. I don't think it's like the displacement gets wrong, but you get weird like stress concentrations around where the force is applied because you get such a tiny element taking on like the whole force or something. Because we didn't distribute it over an area,
so it was just on one node.
so it was like on one end. And then we looked at like when you distribute it over.
Yeah, I mean, I would say I was going to talk about that here in a second. So we can go to that right now, actually.
that has to do with just like force application rather than just like over refine.
Nope, you guys don't want to work at Cruise Enterprises, do you?
No. This is the guys with the mobile batch plant.
Yeah, dude.
The batch plant on the.
Yeah, Tobin and Phil.
Yeah.
Have you done some concrete testing?
Yeah.
Man, you're
They're-
really peaked up here, Sutton. Man, Cruise never on the spot.
They're good tires.
Dude, they're good guys.
Yeah.
I'm designing pre-engineered metal buildings foundations for them here over the next month and a half or so. So, and they're hiring. So, I mean, if you wanted to, okay, it's an option. Overqualified, maybe not though. I don't know. I don't know how practical you guys are. You can handle the pencil, but I don't know if you can handle the shovel. All right. So, I stole this from Adam. Adam said that what he did, right? If he was going to model this silo, wish I could turn this around. Probably can somehow. Not doing it. I'm not worried. I'm not gonna spend time doing it. Okay. So if we modeled this like that guy modeled that building, we attached it to a cliff, right? Add all these silos to the cliff, right? And we wanted to model the cone of this silo. And we modeled it and we started changing the number of plate elements, okay? And we looked at how does changing the plate elements affect our percent error from the converged solution. Okay? Well, as we looked at in our concrete column example at the very beginning of class, right? We're gonna asymptotically start approaching our exact solution, right, our converged solution, okay? And we do that at a different rate with respect to displacement versus our results based on derivatives of that displacement, right? So our blue line being displacement, well, our normal stresses is gonna be based on the derivative of displacements. And so as you can see, the rate at which we converge is hugely different, right? We get 10 plate elements, and we're damn near the converged solution, okay? When we looked at stresses though, holy shit, we gotta be out of like 10,000 plates to get out to that converged solution, right?
What are you converging to?
The true solution. Like converging as in, things aren't changing anymore, right?
Yeah.
Because in this case, we
Oh.
couldn't calculate really the exact solution, we're just gonna try and get to some place where the, like, I was like this. Can't
Sean,
you look at it like
this?
What's that?
You could just
How do you turn it, Jock, alright? Fuck it, dude.
go up to the top left
Top,
for
what?
squares.
Okay,
Yeah.
top right. I select them all?
Rotate on the bottom.
Just like that, that's what you wanted, huh?
One more. Look at that.
Oh, man. You're doing great today, Jacques. Woo!
So did he just not go out even farther with the red line?
Okay, I'll talk
Doesn't
about
seem
that.
like it hadn't really.
I'll talk about that, right? 10,000 fucking plates. That takes a lot of time to compute that, right? At some point, honestly, as powerful as our computers are right now, it'll just crash. There's not enough RAM. The computer doesn't have enough storage to be assembling all of this and holding it there while they're doing all these other calculations. There's just not enough short-term memory in the computer to be holding all the information together and keep going, right? Or you get to the point where, like I mentioned on some of the projects I've worked on, right, it just gets so cumbersome on the amount of time that it takes to run it. It's like you start it and you would hit, run, or you'd make a change and then you'd have to walk away for 3 hours. Well, that gets a little out of hand, right? But you do wanna get down here, right? Well, you wanna get down here only if you're looking at stresses. And you could model it way the hell up here if all you were worried about is displacements, right? And so that's one of the key points here also, is that you have a converged solution when the solution with which you're looking for has converged, right? Because here, I would say that we've converged if all I was worried about was displacement of this model, right? If I was worried about stresses and I kept adding more plates and this thing kept moving down, right? It doesn't converge until I feel like that value converged, right? Or didn't change enough to where I felt comfortable about it.
How would you know when you're converged?
That's up to you. That's beautiful, right?
I mean, if he keeps going down, but you get to a point where it's getting really long.
Yeah.
You
Well,
know,
when
like,
you
let's
look-
just design for a higher stress.
Yeah, I mean, you start looking at the y-axis here, right? 5% error. That's pretty small.
Yeah.
In the grand scheme. I don't know, some of you in the practicing world, in wood design, I don't know if anyone's been like, oh, you're within 10%, you're good. Has anyone said that to you yet?
Oh, yeah.
Yeah, Hicks has. How about you, Sutton?
Yeah, wood's kind of
Yeah, yeah,
a hand
yeah. Yeah, see? So it depends on what you're designing, right? So I mean, if you got down to here, maybe you could do this with 10 plates. You're within about 5-7%. Okay, I feel pretty good about that. We're putting a factor safety of about 1 and 1.7. If it's a connection, maybe it's 2.5. Okay, maybe up to 5. Maybe what we're building already is super over-designed. The architect wants a massive glulam beam. Okay, it's just for looks. Okay, maybe at that point, then it's like, I don't really care. I've done 10 plates, I'm pretty close, it doesn't change that much. It's not gonna change enough to where I'd be worried about it going above what my demands are. You feel good about it, you just continue, you move on.
So the reason for that is because stress.
It's a derivative of displacement.
I'm like still trying
Sleep on it.
to, yeah.
Do you have the NDS built in too?
What's that? Yes. Yeah, you can do
Trust
wood.
that pretty?
I would always do wood design by hand.
It's boo,
What's that?
boo.
Or use EnterCalc.
Yeah, there we go.
Or use EnterCalc. Come on, wood, how many of you have taken wood design?
it would take forever.
See? Come on, easy, right? Pretty easy, kinda easy. Is it easier than masonry?
John asked me about masonry.
Oh, who else is in masonry right
So
now?
we're stuck today.
How'd that exam go?
We don't know.
Oh, you don't know still? Oh, man, rough.
Haven't you finished it?
We haven't even like done any masonry design.
Yeah, no one finished it.
You haven't done any masonry? Oh, you've done like open web steel joists? It's a lot of
Just like a
table work, so you guys should
It's
have
like a spec.
crushed.
Got into masonry.
Just started masonry, 6 weeks left of the semester, beautiful.
I think you're supposed to do the foundations also in that class.
What's that?
It doesn't happen.
Oh, foundations? I don't remember getting foundations. in that
It's
class.
like, at least when I took it, that's,
Yeah,
it was
but
in the
fluctuating.
syllabus, but you never made
Yeah,
it
yeah.
there.
We don't actually do any foundation design really.
What time is it?
In any class.
Okay, we gotta go. All right, this is what we're gonna do. We're gonna finish this really quick. The last thing I wanna talk about is symmetry, right? So as we know, we want convergence. Convergence, we need more elements. Well, one way to get rid of elements is to look at a structure and say, shit, I don't have to model this entire thing. The way it's gonna perform, right? We can add boundary conditions and we can impose principles of symmetry, right? So that we can reduce the number of computations that the computer has to do, right? We took this truss, for instance. We could just model this, right? We model this truss, symmetrically loaded, it's a symmetrical truss. We know that in its deflected shape, right, the center line of this element is going to not displace in the y direction, or the x direction, right? So we would just impose rollers there. It can move up and down, right? But it can't move side to side. And so we could model half of that truss. We would reduce the number of computations that we would have to do, or the computer program would have to do, and we could find ways to increase our ability to then refine that mesh, right?
That's David.
What? I don't think so.
Count your music.
Think so.
It's you saying you think it's David.
I think so. It can't rotate.
It's all rollers.
P over 2, they can have a reaction P over 2 here. They have equal and opposite forces there. I don't know, maybe. You tell me. Huh? Another one would be, we could have asymmetrical, right? Antisymmetrical. Asymmetrical loading where we would result in locations where we might have zero displacement, right? But we'd allow rotation. Well, we could take this loading diagram, right, or this beam, and we could cut it in half. We could model less of it. And, like Adam did here, we could take a cone. Well, instead of modeling the whole thing, and as you can see here, he did 10,000 plates. Right? He only modeled a quarter of this cone. Right? He added boundary conditions to impose upon it the conditions that it would undergo during symmetry. So you're not losing the behavior that you're getting, but you're able to refine your mesh more, right? We essentially can now, because we're only modeling a quarter of it, we can have 4 times the number of plates on this guy than we would if we modeled the entire cone. That would help us with our convergence, okay? I'll post this. When he did this, you can see the percent error in our vertical displacements, right? How quickly we came down with the number of plates. Stresses, though, as you can see, all the way out to 20,000 plates. Right there, you're out of memory, right? The computer just couldn't do it. Couldn't analyze any more plates than that. But in the grand scheme of things, if we look at the percent error, it's like, man, I probably would have felt good way back here at like 10,000 plates, right? Depending on what we were designing, how critical it was.
When was this done? What year?
What was? This? Oh, he did this, he taught this class like in 2015.
Okay. I was just wondering, like, with.
Oh,
computers
changes in
are
computers?
constantly
Yeah,
getting
no,
better,
that's a
better,
very good
better.
point, James. I think,
Like, what would the newest computers be able to do?
yeah, probably a bit more than that. I know visual analysis, one thing that it did is in computer processors, there's actual cores, but then now they have virtual cores, so that it kind of doubled the computing power. So now visual analysis also has the ability to multi-core process, so it takes certain tasks and it splits it up and then it sends it to different processors in the computer, right? So you're always trying to find efficiency. So Visual IES is trying to find efficiencies. on the way that they're calculating things to make sure that the users are able to, if we wanted to use 50,000 plates, let's use 50,000 plates. Right? Nice little mesh, right? Our stresses. Okay. That's it. Be ready, okay? Monday.
How are we supposed to?
I don't know.
So
Get a
how
box
can
of,
we be
get a box of
ready?
Kleenex, okay? Clear those tear ducts out.
Like, there's not much we can really study for when it's open note and
Yeah.
a couple days.
And you probably won't have like, be able to ask you questions as we go on this, but are you gonna be available for like general VA kind of questions? Say?
Yeah, no, I can do that Monday through Wednesday, yeah. You can email me or.
I thought you'd appreciate it, so you're talking about big buildings, this is a house that's,
A house?
yeah, 43